Okay, so this is the workshop 3 video talk through for workshop 3, and this is the part 5 section, and we're starting from step 11. So we have just had a look at the effective windowing, and now what I want to do is go back to our original time series and try and make it a little bit more realistic by including a random noise component. So I've just opened up our create time series script here, and I want to generate another time series exactly the same as the one we've already got, but I want to add a random component to it. So to do that, we just need to go plus rand n. So the rand n is a MATLAB function which generates a random number, and we can give it a length. Okay, so we want it to be the same size as our time series. So we're adding a random component the same size as our time series to our original time series, which had just pure sinusoidal components, and we're going to call this new time series y1. Okay, so we can save that and run it, and we have in our workspace down here, we can see that we have a new time series y1. Now, just to have a little look at compare the two time series that we've got, we'll just open up a new figure window and just have a quick look at what the difference is between them. So I'm going to plot the original one as well, just so we can make a comparison. So I'm opening up the top subplot 211. Oh, undefined function y, that's because we called it y0. Okay, so that's our original time series. Now in the bottom plot, subplot 212, I'm going to plot the new time series, which has got the random component. Okay, so we can see that actually they're quite different, and the one on the bottom is actually quite difficult to see the periodic component. Perhaps if we make it bigger, then you can start to identify periodicities, but particularly during our artificial neap tides, it actually becomes quite difficult to pick out the periodicities visually just by observing it. So there's a lot of random noise in here, and what we're going to do is go through the same steps we've just gone through with our to generate a power spectrum and compare it with the one that for the original time series that doesn't have any random component. Okay, so I'm just going to close that for now. And so we want to compute the FFT and plot it again. Okay, so what we want to do then is to basically generate another script that does pretty much the same thing as this one. So perhaps what we'll do here is save this as plot PSD, and we'll call it random. Okay, so that we know that we're calling the find PSD FFT function, but we're using the one that's got the random component. So in our new script, we need to change y0 to y1. So the input to our function is the time series that's got the random component to it, and perhaps we'll change these outputs as well so that we're not overwriting the original ones. I'll just put an R in at the end. The frequencies will actually be the same, but let's do this anyway. Okay, and we might want to change the title as well, just so we don't get muddled up. So for maybe we'll just say with random component. And then we'll put that in the second title down here as well. So if I save that and run it, let's put it in new figure windows as well. Let's put it in figure 3 and figure 4. Okay, we'll run that. Okay, so there's our power spectrum now. And you can see that the power spectrum is also considerably noisier than the previous one. And what's happened is that the Fourier transform is trying to fit sinusoids to all the random components of our time series, assuming that they're periodic in some way. And of course, it's not able to do this very easily, and so it is actually trying to do it by adding in lots of frequencies, which is why you're getting what we call a noise floor. So there's a lot of peaks and spikes that are from other sinusoids, which presumably, when all added together, make a time series which looks a little bit like our Y1 time series, which has got the pure sinusoidal components, which we can still see those peaks luckily above the noise floor, but it's also got a lot of other energy at other frequencies, which is trying to fit it to the random components of the time series. So what we want to do then is to find a way to reduce the noise excuse me, in our time series, in our power spectrum, so that you can imagine that with a certain amount of noise, it could actually, or maybe less resolution in our time series, it might become quite difficult to distinguish between what are real periodic components and what are noisy, this noise in our time series. Now MATLAB has got a function called pwelch, which actually helps to do some of what helps to deal with this random noisy component to real time series. And it does this by averaging. And so we're moving on to step 12 at the moment. Okay, so we've generated basically this figure here. We're looking at our instructions. And step 12 says, note that the Fourier transform approach for the more realistic time series in step 10 has a lot of variance, so it's more difficult to identify the peaks in frequency. So a method that helps to reduce this variance, so reduce this noise floor, is the pwelch method. And what this pwelch method does, or it's basically Welch's method, but it's a pwelch function, is it divides our original time series up into segments. And for each of those segments, it will apply a window. And for each segment, for each windowed segment, it will generate a Fourier transform. And then it averages all the power spectrum output for each of those windowed segments. And the pwelch function will also overlap those segments as well, so you can get more averaging accomplished within one time series. So step 12 suggests that we open the findPSD pwelch script and edit it so that it is a function, and then we'll try that out on our random time series. Okay, so we go to findPSD pwelch, open that up. Okay, now we want to use the same format for calling this function as we used for the other one, just to be consistent. And we've got PSD frequency. Okay, so we can stick that in front, Control C. And we'll make sure we get the order right, DT and Y. Okay, so we've got DT and Y here. Okay, we don't need the .m, so I'm overwriting that. So we're passing it exactly the same inputs as we do in the findPSD FFT function. Okay, we might need to define a few more things, but I think this video has probably gone on long enough, so I will come to that in part 6.